In this lecture, we're going to start talking about communicating science. To do that, we have to first start with what is science? What is scientific? And then we're going to learn about how to communicate scientific findings that are supported with evidence and at least clearly crafted in a way that someone will actually believe what you're saying. And then the next step is to go on and then start evaluating scientific claims, which we'll do later on. So let's get started. So first of all, the reason we're talking about this is that we use science every single day to make decisions, even when we don't do it consciously. Although, given the current climate that we're living in, we are constantly being bombarded with things that require some level of scientific literacy to really understand. If that's climate change, or if that's different medications in the healthcare system, or just cleaning products, or the pandemic, or nuclear power. It's all going to rely on science. And in most cases, you won't have an expertise level of understanding of the science that the information is going to be based on. And so we're going to start to understand what it means to evaluate something as being scientific or not scientific, and then also think about how to evaluate how something's being communicated to us so we can critically analyze it and evaluate it. So this is just a general chemistry class. This isn't a scientific communication class. However, usually scientific claims go beyond just the scientists of a chosen field. We're not just talking to other experts in our area of expertise. Usually scientific claims are used to form public opinion, and they're used to create public policy. And so just being a well-informed citizen requires us to be able to critically evaluate evidence and scientific reasoning. It's just kind of like a necessary part of being a human right now. So in this class, we really want to practice a few things. We want to practice evaluating if something is scientific, communicating a claim or a statement that has then supporting evidence and reasoning, and then evaluating claims that use scientific evidence. There's a really great short article I highly recommend that's called "I Don't Know What to Believe." It's worth looking at, I promise. Here's the link on the page, and it's also in our Canvas class page. So let's just start with the basics. Let's start with what is science? What is scientific? It's tough. It's hard to define precisely. And that's because science applies to this really broad set of things. Anything from, as I've got here, developing lasers to thinking about how humans make decisions. And I love this checklist of evaluating how scientific something is. It's coming from Understanding Science. It's actually a group of paleontologists, but it's got it's like these check boxes. Like, something scientific checks all of these boxes. So when you're confronted with something, you can compare it to this checklist and ask yourself, does it focus on the natural world? Does it aim to explain the natural world? Does it use testable ideas? And actually, this one's my favorite. Like, are the ideas testable? Does it rely on evidence? And then this is the other one I love. Does it involve the scientific community? Is this one person screaming their idea alone, or are they inviting people to discuss it, to evaluate it critically, and to test their ideas as well? Then also the other kind of check boxes that we have here are, does it lead to ongoing research? So any idea that's testable will inherently generate more questions. And so that would be ongoing research. And does it benefit from are there benefits from scientific behavior? So let's go through and just do a little evaluation. You can choose anything you want to kind of think through this. This is one that I really like doing, which is crystal healing, which is, I've actually got this nice little short video that we're going to show that will have someone explain what crystal healing is. Then we're going to go through the checklist. Okay, we're going to watch a short, like 3-minute video, 2-minute video about defining what is crystal healing. And this is just like an explanation of like what it is. And it's just a fragment of the video to give us an idea to start working on evaluating, is this scientific or is this something that's just not different? So here we go.
Thought to be the most stable form of matter in the universe due to how they are formed within our planet. Crystals grow in the Earth's crust over millions of years at high pressures and heat, making them objects with the most energy, as each step in the formation of a crystal contains energy. The crystal's journey begins deep below the planet's surface, where lava and hot fluids circulate. Crystallization occurs when layers of the planet's mantle fracture, which allows heated gases and liquids forced by high pressure rise towards the surface. Elements such as water, oxygen, sodium, iron, potassium, and magnesium are also present, and in the process they merge and dissolve with other elements being pushed to the surface. As this mixture rises and passes through cooler, less active layers of rock, crystals begin to grow in the rock's cavities and crevices. Crystals will form depending on the specific environmental conditions and the mixture of the elements I mentioned. Growth, shape, color, hardness, and size depends on the temperature of water, light, pressure, time, and space. Crystals are alive like everything else in the universe. They work with the human energy field and are able to diffuse, absorb, move, or shift energy within the body. Crystals vibrate at different levels depending on their composition and color. As do the cells in the human body, they all vibrate on their own frequency, as do the energy centers in our body, our chakra. A video about chakras will be linked in the description. Crystals operate by naturally focusing and magnifying the body's innate energies, dissolving and equalizing emotional, mental, and physical stress. They can alleviate suppressed or unreleased pain and help to make desired shifts in every aspect of one's being. So when we come into contact with the crystal, its vibration interacts with the vibration of ourselves in our human body. First of all, it's not a myth that crystals have energy. Crystals actually have a very high precise rate of vibration and are utilized in modern technology. This includes liquid crystals in calculators and clocks. They're also used in credit cards, phone lines, and lasers for microscopic surgery. Working with crystal energy helps the body to find its natural rhythm and restore its energetic balance. Crystal healing is basically laying of the stones of different vibrational frequencies on your body in order to affect healing or change.
Okay, sorry if that was choppy to watch the video. The link actually in this slide is different than the one we watched. This link has like been taken down, unfortunately. It was a little bit more of a fun of a video because they use the same models that we use in a chemistry lab and classroom. But the idea is the same. So the idea is that crystal healing uses scientific knowledge about the solid state structure of crystals, about how they're formed and the different ways that we can control variables to form different types of crystals. And they do, in fact, like everything, have a vibrational energy to them. Like all energy and all like kinetic energy is going to be vibrations, rotations, and translational motion around a room. And so solid structures have lots of vibrational motion. And then a liquid has both vibrational, rotational, and translational. Same with gases. And so all of this is using scientific knowledge. It also uses scientific knowledge about the physical and mental disease states that humans are likely to have, and so it's connecting these two together. But let's walk through the checklist and see if crystal healing stacks up to what we would consider something that is scientific. So first of all, does it focus on the natural world? Heck yes, it does. Does it aim to explain the natural world? I'd argue that it's aiming to explain how to heal someone or how explain disease states or a process of healing. So this might be true. Does it use testable ideas? Uh, I'll leave this one up. Maybe this is a check mark. Maybe it's not. And you can kind of think about this yourself. Maybe you have some ideas and you can talk about them in the chat on the class Discord. But we can test this if we use crystals in people who are sick in the same way. And then we also have a control population we could compare. So this could be a testable idea. Does this method of healing help a specific disease state? Does it rely on evidence? And here's another one. What is the type of evidence that it relies on? Now, we didn't watch enough of the video and we haven't like dived enough into it. A lot of the evidence that's presented tends to be anecdotal, like a person claims to have improved their condition rather than a study that has a control group to compare to a group that is receiving a specific type of healing. So it may rely on evidence, but it may be of questionable nature in that sense, which will be a little bit more of our next class's topic. Does it involve the scientific community? And so this is one where I would say it does not, because it is not something that you can search and find in any chemistry journals about crystals, right? There's a lot of crystallography journals, and this is not a topic within it. Does it lead to ongoing research? So does this lead to the question of how do the crystals actually do the healing? Now, if you dive into it, you'll find that this part is also lacking as well. So here's parts that are not actually happening. Are there benefits from scientific behavior? I mean, the benefit would be healing. So I would give it that as well. So in this one, we have a few of our boxes checked. We don't have all of them. We have a few that might be checked. And so I wouldn't say like across board, oh, this was some scientific video that we just watched right here. So this is kind of the thing. A lot of things that we're presented with in our day-to-day lives kind of fall into this gray area where it definitely uses science, but is it actually following a scientific process, or is it itself scientific when it's selling itself as such, which is always an interesting question. So a few of these are definitely up to interpretation, and I chose something that would at least be debatable, I'm sure, in most circles. All right. So let's talk a little bit more about the scientific approach to knowledge. And this is a super interesting topic that I'm actually not going to go into a lot of detail here. Instead, I'm going to link to some other videos if you're interested in it. I love this graphic of the scientific approach to knowledge because it puts at the very center testing ideas, that there's this exploration and discovery part that's then like we discover an idea and then we test it and it leads to discovery of more ideas or exploration of it further. Also, we see benefits and outcomes from an idea and then we can test those and then we get more or we refine our understanding of them. We also can see community analysis and feedback, again, looping in with the idea of testing ideas. And all of these are connected. And so, but at the center, it's this idea that we are constantly testing. That testable idea is the foundation of how we approach building a knowledge base. Bozeman Science has a fantastic video on the nature of science. If you have 8 minutes, I highly recommend giving it a watch. And what you'll see in your textbook and in most textbook is really a breakdown of the scientific method, which is a little bit different than the version I learned in 4th grade, and that it got a lot more complicated and has a lot more arrows along the way. But basically, it starts with this observation and curiosity piece right here that leads to a hypothesis. And then we perform experiments to test that hypothesis, and it refines the hypothesis as we test. And then it will refine it more, and then we do some more tests, and that these results are going to then contribute to a body of knowledge if they're consistent with the prediction. That prediction's the hypothesis. I think this will happen. Oh, it's consistent. This contributes to my body of knowledge. These can then ultimately lead to lots and lots of observations that support each other, can lead to a law, and hypotheses that are again supported and supported and supported grow up to become theories with enough evidence behind them. And again, I'm actually not going to go into this in a lot of detail. It is actually really interesting, and I've got another recommendation. Amoeba Sisters did a lovely short video about how we use theory and law in like common parlance and how different it is from like the scientific use of those words. And I think it's worth a watch. So there's a link there too. But I've got a lot of red circles all over this. And that's because I want to point out how much of this scientific process relies on evidence. Like everything is further testing to support or results will be consistent with. And testing is at every single juncture of this flow chart of scientific knowledge of how we build it up. And so that evidence and observation and testing piece has to be central to any of our communications about science. And so when we talk about scientific communication and the style of scientific communication, we're really talking about how do we present evidence so that way it's easy to understand and clearly linked to an idea so that others can critically evaluate it to see if they agree or if it sparks an idea to test something else to test your idea, right? So we're now going to get into communicating scientific knowledge. And that'll be kind of the rest of this particular lecture. And there's a lot of ways to kind of format this, but the most important piece of formatting scientific or communicating scientific knowledge is that it always involves highlighting evidence. Another thing that I think is really important about communicating science is that we always lead with the punchline. We're terrible at telling jokes. You give your idea first and you say, here's the evidence that supports it, rather than a nice slow buildup of evidence with a punchline at the end. So one way to think about a scientific argument, which is like a scientific statement or a scientific claim, is that it's an idea that then would lead to specific expectations, which would be a hypothesis ultimately, and then observations that support those expectations. So when observations and expectations go together, that's like having evidence and reasoning or a hypothesis and evidence that supports an idea. That's when we think we have a strong scientific argument. And all three of these components are critical to making it up. We can't miss one piece of this. And so let's walk through a simple example that I love. All right, here's a scientific idea. Illnesses in new mothers is caused by doctors' dirty hands. Like imagine birth, and if birth occurred without washing hands, or now we wear gloves, and like all sorts of stuff gets everywhere. So if this scientific idea is correct, right, the expectation would be that illness rates in new mothers should go down, should decrease whenever doctors are required to wash their hands before attending a birth, right? Washing hands leads to more healthy moms. So when this test was actually performed, so this is a testable idea, right? We could have a group of doctors not wash their hands and a group of doctors wash their hands. We could see how many moms are healthy post-birth. So it was performed in the 1800s and the results matched the expectation beautifully. Illness rates did decrease when doctors were required to wash their hands before delivering children. So altogether, you put all three of these things together, you have a strong scientific argument. So when we're communicating science, we may have a great idea, we may even have evidence. It's critical to craft our argument or statement so that it is a strong scientific argument. It has that idea, that expectation, and that observation, that expectation and observation that go together. But it also needs to be easy for the reader to evaluate critically. The idea with scientific discourse is that it is open to critique. And so you need to give all the information openly and easily in a way that allows others to evaluate the work and to evaluate the evidence. So to do this, we have a few kind of tactics scientists tend to use in their writing. The most important one is that we always follow claims with evidence. So anything that you state will be supported with evidence. Now, this evidence needs to clearly support the claim, right? Like I can say the sky is blue because there are 14 purple rocks in my backyard. I don't know. I'm making this up off the top of my head. but those two things are not linked at all. So the evidence needs to clearly support the claim, and this is best communicated by explaining that connection, and that's with scientific reasoning. That's what we call it. So the other pieces of this are that there needs to be a level of certainty within the evidence that is clearly communicated. It's not hiding anything. And that statements or arguments need to be open to critical peer review by the scientific community. Someone can come in and retest your idea critically and see if it is still true. So we've shown this kind of idea of what a scientific argument is as idea, expectations, and observations. Another way of presenting it is claim, evidence, reasoning. And so the expectations and observations together are kind of like the evidence and reasoning piece in the second version. The claim is the same as the scientific idea. A claim is like a statement. So in our previous one, my claim would be that doctors' dirty hands are the cause of a lot of illness in new mothers. My evidence would be that when doctors wash their hands, we saw a decrease in illness in mothers. So the doctors washing hands, or so therefore the washed hands that are now clean, and that the dirty hands were causing part of this illness, something like that in the reasoning. Sometimes the reasoning piece seems really obvious to you as the writer, but it may not be obvious to the reader. So here's another recommended link on this topic. Bozeman Science does a nice claim evidence reasoning video that breaks this down really nicely. The idea is that this is a structure or a format for new scientific writers to use to be able to structure a scientific argument reliably. You always start with a claim, a statement about the results of an investigation, or an opinion, or something like that. Then you follow it with evidence. So that's the data that you use to support the claim. And then you use reasoning to tie together that claim and the evidence to show how the evidence supports the claim, how they're actually connected. And this is the style of writing, or similar, if there's a different format that you prefer, that we'll need you to use in your labs in chemistry, and that we'll be expecting you to use in short answer responses as well. So here's just an example based on movies. And I've highlighted this out. So our claim is the very first part right here. The most popular movie of all time is Gone with the Wind. That's the claim. The evidence is in orange right here, because it was the highest domestic grossing movie after adjusting for inflation, earning over $1.8 billion in adjusted gross income. Right, so that's evidence. That can be evidence of lots of things. So we're going to have reasoning that clearly ties the two together. The highest earning movie indicates a large number of viewings and therefore popularity. And so what it's doing in the reasoning piece a lot of times is defining terms. In the claim, I said that we're talking about the most popular movie. In that statement, like, what does popular actually mean? And so the reasoning piece is saying, well, popular is going to be indicated by the number of viewings. As a critical reader here, I could say, well, I actually think popularity, instead of being the most viewings, is really about the largest net gross, not adjusted, or it's the most popular compared to and adjusted for the number of movies that came out that year. I could argue that not that many movies were actually out in the theaters when Gone with the Wind came out. And so it was easier to be a big fish in a little pond than many movies today that have to compete against a much larger pool of options for viewers. Claim, evidence, and reasoning. And they're going to go in that order. Give me your statement, give me the direct evidence for it, and then explain how the two are linked. All right. You're going to do this in post-lab questions. You're going to do this on exam or problem sets and the short answers. You're going to do this in class discussions. This is something we're going to practice throughout chemistry. So that way we develop our scientific communication skills. You'll also use this in other areas. Sometimes it'll be called something different. but we'll always want to make sure that any statement we're making or claim that we're making is backed up with evidence and explained.